In this video we discover point-circle collision detection. Although testing only a point in space is very inaccurate and could cause strange glitches, but it is also very efficient and fast to compute and lays out the foundation for other collision testing methods. My name is Alex and this is another video in the series about collision detection for 2D games. So let's get started. First, we start with a point P that we would like to test against the circle. The point is represented by a simple vector. The circle has a center C and a radius r. The most obvious method to go with is to compute the distance vector d that we could use to measure the distance we are away from the circle center C. So the vector d is computed by a simple vector subtraction like p minus c. The next observation we can make is to simply relate the length of the distance vector d to the radius. Since computing the length involves a square root to compute, which is never desirable if not required, we could square the equation, so we can compare the squared distance d to the squared radius r. By squaring the equation we end up with an implicit function that can be evaluated by inserting the data we already have, that is the point's coordinate and the circle's center point. Then we can compute the function shown. Thinking in vectors, we could also compute the scalar product of the distance vector d itself. So d upper TD gives the same squared result that can be used to compare against the radius. Having the distance value, we can simply compare it to the radius. If the squared distance is greater than the squared radius, the point lies on the outside of the circle. If the squared distance d is less or equal to the squared radius, the point lies on the circle's contour or inside the circle. That's already it. The point-circle intersection testing is very simple and very quickly computed. If a collision response is required, we also need to be able to compute the surface normal. This is done by using the unit vector in the direction of the distance vector d. Normalizing the distance vector d will yield the circle's normal at the approximate hit location. You could build a Hesse normal by inserting a negative radius in the third component of the normal vector. For the video we prepared a sample application that can be found on GitHub in the description. The application shows a big and a small circle. The small circle represents the point but is rendered as a small circle. It is also attached to the mouse. Its position is updated if the left mouse button is pressed. The application tests both primitive against each other and determines the intersection point along with the response normal. When the point approaches the circle, a distance vector in green is drawn. That vector is used for intersection decision. If the point touches the contour of the circle, an intersection point is drawn along with the normal. The sample also shows the flaw of just testing a single point. That is, if the point penetrates the circle a lot, the wrong normal is computed due to lack of information. So the response of the intersection would reflect the point particle in the wrong direction. This can be fixed by using rays, but that topic will be handled in another video. That's it. This was a very short video about point-circle collision detection. Testing a point against a circle is very simple and it can be used to quickly test any collision. Until next time, bye now.